Okay, so this is officially the last lecture of the semester, but I would like to continue lecturing maybe at least twice. I think twice after in June, and I was discussing with Andrew, and it seems that Friday in 2 weeks it would be a good date. So I don't know what is Friday 8 maybe, or I think Friday 8 of June. Is this okay for everybody? Yeah. And so then afterward, I think maybe let's say, I mean, we decide this later, but maybe the Wednesday after would be the last lecture. Okay. So, good. So I continue with what I was doing last time. So remind you that my goal was somehow to construct a purely algebraic model of this quotient of omega that we were trying to construct, and I introduced some tools around stratified schemes, regular stratified schemes, and so I want to continue with this today. So so this will be paragraph 6.3. So I'll discuss about, so again, around the notion of regular stratifications. Three, and this will be about topologies. Okay. So here's a general principle or a general definition. So if you are given a topology, so if tau the topology on Noetherian scheme, or maybe excellent foliation, so then a family of stratified morphism is called, so is a cover, or is a tau cover, if it is so after forgetting stratification. Forgetting the stratification. And so in particular, you see if you have, if you take the identity map between X and the stratification, going to X with another stratification, if S prime is finer than S, then this is a cover. This would be for any topology. Okay, so, and I'll be mainly interested in the case of the H topology, in fact. So maybe before also, so of course, as usual, the same thing also apply for star objects. So if I have, again, a morphism of star schemes, then I call this a tau cover if it's so after forgetting stratification. So the main in this, so the main topology that I'm interested in is the H topology. So we will be interested mainly in the H or H star topology. And we have the following first observation. I put it as a lemma. Okay, so let S be case finite, let's say finite type scheme. And here, as usual, but let me stress the characteristic of K is supposed to be 0. So there are two parts. So the obvious inclusion induces an equivalence of sites, and the obvious inclusion is the one from yeah. So I write it in the opposite direction. So finite type schemes over S for the H topology. There's a morphism of site that goes to regular for the H topology. So this is given by the inclusion of regular schemes into schemes. So this is an equivalence of sites. So it means that it induces an equivalence on the topos. And same for the stratified version. So let me write it. So if I put sigma with the H topology, and this is the same or equivalent to the regularly stratified versions. Okay, so this is very easy. It's just in case you haven't seen this before. So A is classical. It follows from resolution of singularities. Which tells that any scheme of finite type over the field can be covered for the H topology by something which is smooth. And B is same. Again, it follows from resolution of singularities. Here, just we need we need a bit. We need slightly more. We need to know that we can also refine the stratification so that it becomes irregular. Right, so we also use resolution of singularities to get a regular stratification. But it's again it's the same thing. The fact that you can cover for the H topology anything by something which is regular. Right, so this is. Of course, it is. I should say maybe here that so this is a nice site because it has fiber products. This does not have fiber product, of course, because you destroy the property of being smooth. So it's technically maybe easier somehow to think or to work here, but we will see, for instance, examples later of presheaves that are naturally defined. I mean, for example, the presheaf omega is naturally defined here. But not here, or here it's not such a nice presheaf, and so it's good to have this kind of statement, right? So it allows you to extend a natural way something from here to there. Okay, so also in the same spirit, we have the following lemma. Again, so as before, so the obvious inclusion, sorry, let's give a name to this. So let G be the functor from scheme of finite type to scheme of finite type stratified. So this is the obvious inclusion. Which what does it do? It takes x to x with its coarse stratification, namely the one given by connected component of x. So then also G induces an equivalence of sites let's also say so for the H topology, but here actually H is not really important. In fact, for any tau, as I defined before, it will also work. Just put for the H topology. Okay, so let me prove this. So again, this is somehow a general fact. But so to prove it, it's maybe one way is to do as follows. So we introduce another functor, which I denote by O. It goes from the opposite direction. And this is given by forgetting certification. It's a forgetful functor. And so this is actually the I think the right or the left adjoint. So this is left adjoint to G. And so in particular, this and even and also we have, I think let's see which one. If you compose so the G and O, you get identity, right? If you take a scheme and you put the coarse foliation, the coarse certification, and then forget it, it's just itself. Okay, and so what we need to check is that so this adjunction OG. It induces also an adjunction O star G star on H sheaves. Right, so it's kind of clear that these two functors they are continuous for the H topology. So and so by this we get also that this is identity. So we are left to check that G star composed with O star mapping to identity is an isomorphism, or it's maybe the map goes as fast as this way. Okay, so we check this. So and it's enough to check this on representable. So i.e. H sheaves that are associated to a finite type scheme X. But so in this case, the map. So the map is then given by it's a stratified scheme. So the map is then given by just the obvious map. Right, so the stratified scheme going to the coarse version. And of course, you have to put AH here. But then, so I'll have to check that this map is a bijection or it's an isomorphism of sheaves. And this follows from the fact that it's clearly a monomorphism. So if you forget the sheafification, this map is injective, of course. It's a monomorphism, but it's also a cover because yeah, this is a cover of this. And so it's surjective H locally, and therefore it's an isomorphism in the H topology. Okay, this is there are probably a different way of stating this, but and as you see, we don't really use the H topology here, contrary to the statement. And for any topology for which we have this fact here that this map here is cover, the argument also works. Yeah, also give a remark about these functors here. Okay, so this functor O star from let's look at it on pre-sheaves. So it has a very simple description. It does the following. So if you have F, which is so pre-sheaf on stratified schemes, then the image evaluated at the scheme X is simply given by taking the co-limit over all stratifications of F evaluated at X. And this is it follows, for instance, easily from the construction of the inverse image along a functor. And so by the proof, so we know that, so since we have this adjunction sigma upper star G upper star, we know that G lower star no, sorry. Since we know that these are equivalences, inverse one inverse of the other, then in fact, so G lower star, but only on H sheaves coincides with O star. That's all. Okay, so let me now just state the following corollary, which is really what we will use later. So this is somehow follows from the previous two lemmas. So again, S of finite type over a field of characteristic 0, say for simplicity. So we also denote by G the functor from regular schemes to stratified or regularly stratified scheme, which is again given by the obvious inclusion. So then G upper star, or then this induces an equivalence site for the H topology. Okay, so at the end, somehow the four styles that I introduced here for the H topology, they are equivalent. Here, of course, again, the fact that we are working for the H topology is crucial because we use the first lemma. This will not be true without taking H, I suppose. Yeah. Okay, so this is combining the two lemmas. Just a small remark about how this will be used. Just make two remarks. So the first remark is, so we somehow what we are aiming to is, so we would like to construct, so we want to construct some complexes of pre-sheaves on, let's say, schemes of finite type, maybe, over some base. Or even maybe smooth, or even regular scheme over S. And so, so this is what we would like to get at the end. And we will get to this by first. So so to do this, we will first. So it will be easier somehow to first we will construct such a thing on this somehow much more rigid category, which is a category of finite type regular scheme with a stratification over S. So somehow here there are less morphism, if you want, and somehow this is a category which is relatively more rigid than this one, and there will be we will see some construction which only makes sense here, and then we will use this corollary somehow to transfer what we have, so the pre-sheaf that we have here to one which lives here. And so this is somehow how we will use this corollary. And the second remark is that so the previous facts are also true for star objects with the same proofs. And here, so with we use a HA star topology. All right. Okay, so the next topic today will be about the notion of flaggy presheaves. Or maybe better, presheaves on flags. So the so this somehow will be needed to generalize the construction of the Godmore resolution. So here the goal is to define Godmore type complexes in more general situations. And so I work from the start in the context of star schemes, because this is what I will lead later. So work with star schemes, of course, but everything also somehow makes sense for just simple schemes. So I need to define first the notion of flaggy presheaf. So okay, so let's fix from now on just base star. So a flaggy presheaf on some subcategory V of finite type stratified schemes over P star. So this is simply a presheaf on the category that I've seen before, which is the integral of V of flags. So maybe I can write it like this: of flags of x1. Okay, so this means that, i.e., given a pair of star scheme and flag, we associate to this an object f, which I will usually, at least there are, it uses confusion. I will simply write ft. Of course, it depends on x, but we write it like this. Okay, So this is notion of flaggy pre-sheaf, and as you imagine, this you can now repeat the construction of the formal Goldman complex in this situation. So very quickly. So now, if f as before, we associate an augmented or co-augmented co-simplicial pre-sheaf on the category V by so that I denoted by F, and let me just tell you what is the mth term at a stratified scheme X. This is the product of overall flag morphism of flags, sequence of M morphism of flags of F. As usual. So I should put the star. Yes.
This fact that you wrote x1 there was because the flags were only defined on x1, and then one or the other were in a better plane.
Yeah. So.
So these pre-sheaves should depend mostly on x1.
No. They depend also on x0 and the certification. Yeah. I mean, so even if I write it like like this, FD, as I said, it depends on X star, and in particular on X0 with its stratification. Okay. So the flag D determines the flag on X0, but still somehow X0, and we see examples where the value F depends on really on X0 also. Okay, so let me just make a link with what we the similar construction that we've seen before. So now here we start with F, a complex, or it's pre-sheaf on the category of excellent foliation F over P star. And so to this we define the flaggy appreciate that I denote by f hat by setting f hat of d, or let me here write x star. So by defining this to be the value of f at the completion of x star at d. So of course this makes sense for any excellent foliation, but I want to restrict this restricted to finite type schemes. Just to be really in the previous definition. So this is an example of a flaggy pre-sheaf. And so with the notation of a previous lecture, so we have that so this Godman complex associated to f hat evaluated at a scheme x with x star with its natural stratification. This is given by, so it coincides with the Godman complex x star of the stratification of x, this value in f. So this is the previous notation. And this is somehow the new one. Okay, so to continue with this, we have the following lemma. Again, just to make a link with the formal Godman resolution. So same notation as before, same notation, same as in remark. So the following two co-augmented co-simplicial objects are the same. So the first one is the sheafification for the HH star topology of the formal Godman complex. This is what we were considering last time, restricted to finite type schemes. This is on one hand, and second is again HH star of the Godman complex, but associated to this flaggy pre-sheaf f hat. Now, see, these two things are not really they're not really comparable objects, because this is still this is a pre-sheaf on stratified schemes, and so to be able to compare them, I restrict via G lower star. Okay, so these two are the same. So basically, this uses somehow the remark saying that G lower star is also given by O upper star, which is taking the co-limit on all stratification, which is something which is hidden in this definition here. Okay. Is this clear? Yeah, so the notation are not so great here. Okay, let's see. So this was defined last time, I think. And let me remind you what was this. So this was, so at f, this was a colimit on all stratification of x of the Godmont complex of the stratification at f. Okay. So this works for a presheaf on excellent foliation. Here, f is a flaggy presheaf, so it's somehow two different kind of objects. Okay. And somehow from now on we will only use this kind of situation. Okay, so now I have all the tools to be able to describe this the algebraic, the purely algebraic model of omega. So purely. It's clear. Okay, so let me again, just to fix some notation, remind you of the situation. So we have this map. So far we have constructed the following map from omega to some map of spectrum. And this is applied to the Godmont resolution, to the formal Godmont resolution. So this is the one in one here from, and this is applied to this T spectrum sigma bar T infinity of a presheaf complex of presheaf W, which lives on excellent foliation, and all this is made fibrant for the HH subtopology. So this is what we have so far, and this is it lives on excellent foliation, but I want to restrict this, so we restrict this now. Finite type scheme over P star. Here, to be precise, it's this diagram of schemes, P star omega n. Okay. And so what I want to do is really to get rid of the completion that are apparent, that are hidden here. Okay, so first let me use this lemma. So by the previous lemma, we can replace, so after restricting to finite type schemes, we can replace this here by the following. So this part here, I can replace it by G lower star of dot the Godmont complex, but now on this flaggy spectrum. Okay, so here just I take level-wise the spectrum and I associate to it its hat, flaggy presheaf version, and then I apply the Godmont complex, and this has to be made fibrant again. Okay, so this is what we have now. And so now, the next step is to replace. So the next step to replace the flaggy pre-sheaves this one. So okay, so flaggy spectrum maybe. By a purely algebraic one, i.e. without completion anymore. So this is what I want to do in this section. And so this somehow we can break the problem in two parts. So at each level, this is a tensor product of two simple things, namely, so we have O star bar. Right, this is where there is a bar here, I think. And then taking the associated flaggy presheaf, and then and this is maybe the more interesting one, is the heart of y. So we need to replace these two things by more algebraic versions. So I first deal with y, which is a more interesting case, and I want first to maybe remind you, or at least rephrase the way y was constructed. Okay, so maybe start with the following definition, introducing a bit of terminology. So we can also speak about flaggy two functors. So let me say what it is. So a flaggy two functor is what you imagine. So it's just say on a subcategory inside finite type schemes stratified over star. So it's simply a contravariant two functor from so let's call it V from the integral of over the category V of flags to some category. And given, so as usual, given x star, there we simply write the values of this two functor value. And we can also speak about flaggy presheaves with value in a two functor. So if I'm giving such a thing, so a flaggy presheaf with values in V is what you imagine is the data, or it's a function which take a pair to an object that belongs to VD. And plus, whenever you have a map, an arrow from, say, y star you get an induced pullback map from the inverse image of FD to FD. And this is what is a what is a pre-sheaf with value in a two-functor. Okay, so we will be dealing with things of this kind. Okay, so with this definition, I want now to recall the construction of y. Just rephrase it in using this terminology here. Okay, so let me give you some examples that would be relevant. So here's a remark. So we have already seen an example of a flaggy two-functor, which is denoted by make with a hat, and so it goes from finite types scheme, which are endowed with an affine stratification over P star. Cut. And this takes a pair like this and sends this to the category of module with integrable connection on the completion of x at the flag D. Okay, so this is an example of a flaggy two-functor, and we have also seen an example of so we have a flaggy pre-sheaf, which I denote by y hat and underlined, with values in make. And how this is given? So with previous notation, this is evaluated at a flag D in some x hat. This is given by y x completed at x star completed at D. Well, there's a star this we have seen before, and I will maybe recall it later, unless you want me to recall it now. Okay, so this is something we have seen before. This guy. Okay, so and remember this is of logarithmic type. And then with these two objects, we can go. So let me go further. So we also have a pseudo natural transformation that goes, which is a drum complex that goes from this flaggy two-functor to the constant two-functor, which with value complexes of k-vector space. And what it does simply, it takes a modulus integral connection to its Durham complex. Okay, so with this notation, then y, the thing that we are interested in, it's not anymore on the blackboard. So this y hat is simply given by the Durham complex applied to this thing. So this will be by construction a flaggy complex, will be a complex of flaggy pre-sheaves. So this is our y, and so this is what you want to somehow what you want to do. We want to get rid of the completion in the construction of this. Okay, so we are close now to. Okay, so let me introduce some more notations. So if X is a smooth finite type scheme, denoted by make regular singular X, this is subcategory make consisting of smooth modules with integrable connection on X with regular singularities at infinity. Okay, so last time we have seen a version of this where I put the boundary. Here it's the absolute version, which makes sense for a smooth scheme over a field. So we just fix any compactification and take regular singular with respect to the boundary of this compactification. Okay, and I also want to consider the big version of this. So this is, if you want, the int category of the small one, but also you can think about this as object in make X, which are union of mi, where mi are in the small. So it's a modulus interval connection, which you can write as a filtered union of its submodule which have regular singularities. Right, so this big MIC is the int category of the small MIC. What?
I and the C, just that is a different
M, big I, big C, regular singular, big small, I don't know, small MIC, regular singular X. Here there's no regular singular. What is the problem? So when I write small IC, this is a small category. This is a category of locally free of finite rank modules with integrable connections. With the big IC, it's int object in the small one. Okay. Okay, so we have somehow the analogous remark. So again, we have a flaggy two-functor. Now it's not anymore on oh yeah, I mean, okay, no, it's the same. I should maybe have said it here. So here I don't need actually to restrict to regular schemes. This construction makes sense without this restriction, I think. No. Yeah, I was saying that I don't need to have regular there, but actually I do. But I don't need to have regular certification. So this makes sense without having regular certifications, because I'm only completing along things, and this is so this preserve the notion the smoothness thing. So there's no. Okay, for this remark, yeah, I could. So this is somehow extend naturally to general certification. But for this, I will have to really to consider only regular certification. Okay, so we have this flaggy two-functor, which I denote by which is given by MIC. Okay, let's put the big one, MIC. Regular singular, composed with M0, and so this goes from flags and takes a pair like this and send it to the category of module with integrable connection, regular singular, over the open stratum M0 in X0 of the push forward of the flag D. Maybe I should. Okay, so you have your flag which is on X1, you push it to X0, and you take this associated, if you want, open normal cone, and then you take modules over this guy. And so we have seen that we have exactly the right functoriality to make this into really a functor. Okay, and moreover, so by the last theorem from last week, we have a pseudo-natural transformation that goes from. So I mean, here I do really need to restrict to regular singularities because here it's hidden this construction of the limiting limiting module with integral connection, which only makes sense under this restriction. Okay, so we have a natural transformation like this. Okay. Yeah, and moreover, for a fixed d inside from x star, the functor from make so this is 0. Did I put star somewhere? I don't remember. This is, yeah, it should be 0 if there is a star somewhere. Like if I wrote mic x hat stars, this is wrong at some point. Is there something? Yeah, it should be 0. It's on the zeros, not on 1, not on star. It's really modulo over x0. It's not the same 0. I mean, this is really 0. This is circ. That is 0. Okay. So for such a d, this functor induces an equivalence. An equivalence between the submodule of logarithmic type in each case. This is not surprising. It's because moduli of logarithmic types are very simple, and you can somehow describe them using invertible functions on your schemes, and it's not so surprising that the invertible functions here are the same essentially there. Okay, so yes. Yes, this is completion of x0 along the flag image, direct image of d. Okay, so yeah, so because we have this equivalence, it follows that we can transport back this flaggy pre-sheaf with value in mic hat to something which I denote by y underline without anything, which is flaggy pre-sheaf with values in this more algebraic version. Okay, so On the other hand, we have, or we also have, so moreover, we have a pseudo-natural transformation that goes from make regular singular composed with n circ to vector spaces, modules over k, which is given by, so I denote this by gamma 0, gamma delta. What it does, it takes a module and sends it to just morphism between the unit object and it. So this is like a global section functor. Okay, a global section, and it gives you a natural transformation, and it admits a derived version or gamma delta, which now goes to complexes of k vector spaces. All right, so with this, I can now state the main theorem of this section. Okay, so there exists a natural morphism of complexes of flaggy presheaves that goes from R gamma delta applied to y, which is the flaggy presheaf with values in mic regular singular composed with m, to the y hat, which, remember, this is the ramp complex of y hat underlined. So this is flaggy presheaves on regular finite type, sigma f affine. This is, of course, only defined up to quasi-isomorphism, so well defined. So it's really in the draft category. Okay, so there exists such a thing, but of course this is not precise enough. So moreover, it induces an H star local equivalence when you take the associated Goldman complexes. and this is also after twisting by any f. So I write it down. For any Laggy sheaf or complexes. Okay, so differently, this is as good as that one in some sense. So we can then forget about this and only work with that, which is completely algebraic as you want. Okay, so let me say a few words about the proof of this theorem. So maybe before saying something about the proof, let me just comment about one thing. So you might object, or you might think that there is no reason to take this derived functor here, and one could rather really just, as we did before, apply somehow the Durand complex to go to complexes of modules instead of I mean, of course, the derived home from 1 to something is closely related to the Durand complex, right? It's not always it's not the same, but it's really somehow morally quite close. Okay, so you could ask why would I take this instead of taking the Durand complex? And there's a good reason for this. Is that the Durand complex will not give you a pseudo-natural transformation, and the reason why is that in the inverse images functors for this 2 functor, there are these psi functors, this limiting construction, and this limiting construction do not commute with the Durand complex. So if you had only inverse images, then it would be fine to take the Durand complex. Okay, so since we don't have we have these psi c hidden here somewhere, we cannot take that one, so we work with a different version. Okay. And somehow, really, the essence of this theorem is to say that it doesn't really matter to work with omega or to work with R gamma delta, at least locally for the HH topology. Okay, let me comment a little bit about proof. So yeah, I said the Durand complex is closely related to X. In fact, it is indeed the same if you work with the big category of module with integral connection. So this is a simple fact that the Durand complex of a module with integral connection really computes the R home. So if we take the big category, this is quite simple. This is simply because you have an explicit resolution of 1, and then you use it, and you see immediately the Durand complex appears. So So this implies that we have a morphism of flaggy complexes of free shapes. Why? Because I could replace omega there by R home one, and then it becomes really just obvious functoriality of the construction. Okay, so this gives R home. So then somehow the maps now are given by this. So I don't know. If I give a name, but maybe it's clear enough. So okay. So this is why we have such a map. And now let me just say a few words about why this would be an equivalence locally for the HH topology. Okay, so all right. So to check that we have indeed an HH star equivalence, local equivalence, as usual, we evaluate at points. So we pick at V star, which is a star polytray in the category of so type over P star. Okay, we fix such a thing, and we evaluate our complex at this point. So I will not tell you, but you can imagine what we get at the end. So we are reduced to show that so that R gamma delta of y evaluated at some flag in V. So this will be a flag in V1. Or I mean, I can really write it like this, actually. I evaluate this guy. And yeah, so this R home. Now I really work module integrable connection, regular singular. 1 with value here, 2 R home, the big one without any condition, again from the. So we want to show that this is a quasi-isomorphism. Okay, so we want to show that locally the ramp cohomology is computed, compute the X groups in this smaller category. Okay. And so since these two are modules of logarithmic type, they are extension of trivial ones. So in fact, at the end, I can even reduce to that. Okay? So we need to check this. Okay, so now remember that we restricted ourselves to a finite type schemes. So there is no more foliation, no more completion, nothing, just finite type schemes. And now, if you think a little about what is this object, so M0 V star at the flag gamma. So what kind of object this is? This is simply, you can think about this. A good approximation is that this is some kind of affine, so some kind of a product of GMs times the spectrum of some field K, which is a finitely generated extension of K. And in fact, K will be simply the residue field of the smallest stratum in V0, which is the image of psi 0. Okay, and so we want to check that on such varieties we have this isomorphism, and it's indeed true. So the results follow from a theorem or from a lemma due to Beilinson, which tells us that I mean, I can maybe more generally say that the obvious functor from, so in this geometric context, so K is the field of fraction field of variety, the functor going from the boundary derived category of the module with integrable connection, regular singular over K, to the thing that I denote by this dBRS make over K is an equivalence. So here this is what this is. So you take the derived category of the big category of modules with integrable connection, and you look at the full subcategory consisting of object whose cohomology is regular singular. Okay. So this is classical lemma of Beilinson, which gives what you want. Okay, so this was somehow the case of y, and we still need to somehow take care of the other factor that constitutes the spectrum, namely the O star factor. And so this is rather simple. Let me explain this. So we use the following lemma. So we take X to be regularly stratified affine foliation, which is complete along its closed stratum. Which I call by C. And assume that C itself is a smooth finite type scheme. C is a smooth finite type scheme. Okay, then there exists an isomorphism, canonical isomorphism between O star X0, so the open stratum in X, and invertible function on the normal cone, or the open normal cone. Let's see. So it's very simple, and I'll just explain to you the proof of this. Yes.
Do you assume C is a closed triangle, or is the completion of X along is closed triangle?
No, X is complete.
Okay,
X is complete along C. Yeah. So C is the closed stratum, and X is isomorphic to the completion of X at C, if you want. Okay, so yeah, so I construct a map, and then it becomes quite clear that this is an isomorphism. Yeah, so the point is that if you have U in O star x0, right? So you can look at the divisor of U, and so this is a Cartier divisor which supported at the boundary. So this is it's in particular it's an element of this. So by definition, it's an element of this lattice that I denoted Rx C last time. Okay, now remember that another way to define this open normal cone is by saying that this is a spectrum of the graded algebra of over element of this Rx C of I bar V, where so I bar V is this IV over the sum over all V prime bigger than V, and this IV is ideal of the Cartier divisor, or maybe the inverse. It depends on conventions. Okay, so this is okay, and so of course the natural thing to do is as follows. So now know that U is a generator of IV, I div U, and so what we do, we just send this to U bar, which is its class in I bar div U. Okay, so and this it's clear that this is a multiplicative map, so it's compatible with multiplication, and this gives, so this is a unit over here. So this gives a map from like this. Okay. But then it's also clear that this map factors through this quotient, essentially by the functoriality of this construction and the fact that that the image. So yeah, should I think this is clear. I mean, so what I'm saying here is that if I take an element of the form 1 plus f corresponding to a map from x to kt, then this will goes to 1, and this is simply by the functoriality of this construction, because if you replace x by spectrum of this guy here, then the image of 1 plus f will go to 1, obviously. Okay, so and it is also surjective, and yeah, then it's somehow essentially enough for this proof. Okay, so as a corollary of this, was yeah, essentially there exists an isomorphism of Flaggy-Prishev between this O bars hat and simply O star composed with M circ. Okay. So also somehow this part of the spectrum completely algebraic, becomes completely algebraic. Okay, so let me finish this paragraph with somehow restatement of what we have up to now, and we start with a remark. So I want somehow to say what I want to do now is I want to again for the nth time recall the construction of. So now what I will do, I will restate or recall or redo the construction of this guy omega, without referring really to completion, because the way I mean, if you remember, the way I introduced this is by saying we have an equivalence between two functors, and we can somehow take this y hat underline and get this y by pulling back of them. So I want to now give you a description which does not use this equivalence. Okay, so to do this, I need to somehow go a bit to the beginning. So let's see. Let's give, so given a pair I alpha in this indexing category, so we know that the scheme E alpha is endowed clearly endowed with, and that was it was a natural stratification. There's an overline. Right, so this is a product of E bar 1. Okay, so given a stratum in here, so there exists a unique quotient map from alpha to something which I denote by alpha c, such that, so this will be surjective, such that the induced map so identifies C with E bar alpha C with the open stratum here. And in fact, so it will be an isomorphism between C and between the closure of C and this guy. More, of course, also more generally, or let's say, given a flag, we denote by, or we set alpha the flag to be alpha of the largest stratum. And so, again, it's not difficult to see that there exists a canonical identification between m plus E bar alpha of this flag and E bar alpha the flag. So we have this kind of. Yeah, this is very easy. It's just you have to think about it yourself for a moment, and you see that we have this. And now remember that also that we have, so remember that we had natural modules with integrable connection that were denoted by n. So here it will be alpha maybe C on E bar alpha C, which I identify with n0. Yes. Okay, so this gives us flaggy three sheaves with values in the following two functor: integral over I alpha in the indexing category, flags E bar alpha to cat sending I alpha C to module mutable connection logarithmic type over M0 E bar alpha C. Okay, so this is just or thinking about these modules we constructed before in a slightly different manner. Okay. Okay, let's continue with this. So okay, so here now let's fix x star, p star, alpha scheme, which is regularly stratified of finite type. And so, as usual, we consider in the diagram of this form. So I have e bar alpha. So I have x1 going to x0. This is the projection that I call px. This lives over the base, which is e bar alpha ai. This was denoted by rho. And I give a name to this map, qx. And this is just the composition of this map projected to the first factor. So we will. So I say orally. So I assume that this guy is stratified, so that stratification is fine enough, so that this map is a morphism of stratification of stratified schemes. Or qx rather. Okay. Now, say given flag on x1, we have the following diagram. That's the following. Yeah, we have. If you want this, yeah, we have the following morphism. So we can go from. So we have this m plus e alpha qx star d have m plus x1 t, and then I have m plus x0 px star. And then this is, I denote this by qx, and this is px. Okay. Okay, so, and then we, from this we have also, so we now apply the two-functor MIC, regular singular, to this diagram, and I put m0 instead of m plus, and then here I get the inverse image functor. Again, m0 instead of m plus, and this is px upper star. Okay, so we have these functors. We also have a right adjoint, px lower star. Okay, and with this notation, then we have that. So this y underlined d underlined. So this is the one that I wanted to. This is the guy that I want to describe. Is given simply by px lower star applied to qx upper star applied to n of the flag qx lower star t. Okay, so this is okay, this is a description of y that I wanted to give. Okay, so you see this is completely algebraic. Okay, so let's continue a little bit. Okay, so now that we have this flaggy pre-sheaf, so we pass to this, we apply our gamma to it, and this gives us the complex of flaggy pre-sheaf on regular finite type stratified P star. Okay, so we also have O star composed with M that I denote by O star tilde. So this is also the same. It's a complex of flaggy pre-sheaf on this guy. Okay, and so we set Z tilde M to be the Godman complex, which is associated to O tilde star taken to the power M, tensored with this guy. So this gives a T spectrum on the category of regularly stratified varieties or scheme over P star. Spectrum denoted by simply by C tilde. Okay, so with this we have now proven the following theorem. There exists morphism of T spectra on smooth varieties like this, from omega representing the RAM cohomology to thing A1 composed lambda infinity, then composed with dot and theta r of pi lower star, p lower star, and now I put g lower star of the spectrum C tilde made fibrant for the HH topology. Okay. All right. So this is what I wanted to get, namely this. So this quotient of omega, which also can be written in a purely algebraic way. Okay. So yeah, maybe let's take a break, and then I continue afterward. Okay, 10 minutes break.